to transformers and transmission. The first chapter, you learnt how forces on a wire loop can be used to spin that wire loop and create an electric motor. And in the next chapter, we worked out how if you didn't put a current through that loop and instead attached, say, a little handle and cranked it around in a circle, that you could use the same apparatus to create electricity in generation principles. But once you've created that electricity, you need to kind of know what the next step is. And the next step is taking that electricity and delivering it to people who use it. You know, you and me, factories and shops and things like that. Okay? So what I've got here on the board is a really stripped down basic version of how the whole process works. And what we're going to do when we go through these notes is you're going to have a look and see at each stage what are the most important aspects of getting electricity from one point where it's produced to another point where it's consumed. Here is a nice coal burning power station. We love those here in Australia. So this guy here is creating the electricity by burning some sort of fuel and boiling water, using it as boiled water, spinning turbines. The turbines then spin generators or alternators and create electricity. Okay, so they produce electricity. That electricity comes out at a certain frequency, and as we know in Australia, it's 50 hertz, and at a certain voltage. I'm not sure what the voltage that it comes out is. Doesn't really matter. Once that electricity comes out at whatever voltage it is at, it's actually too low for transmission. Remember that whatever power that the station is supplying is a set figure. Power is the rate of delivery of energy. So that's why its true units are joules per second. Okay? So if you create a joule of energy, or not create, but produce, a better word. If you produce a joule of energy, then that joule of energy exists and you can't simply make it disappear or waste it or use it up until it's gone. All it does is it transfers from one form to another. So when we say how much power we're producing, we say how many joules per second. So let's say we're producing 1,000 joules per second, or what we would call 1,000 watts of power. Then 1,000 watts comes out. The game here is to get as much of that 1,000 watts all the way over here to my house as possible. Okay? So, if you transmit it at low voltage, at comparatively low voltage, then what will happen is that the resistance in these lines will be enough to pretty much dissipate a lot of that energy into the atmosphere through heat and the humming noise that those lines make. Alright, so that's where the energy is often lost to other forms, and what you really want to do is avoid that. So what we've found is that if we produce a certain amount of power, okay, let's say we put in 1,000 watts of power into the system, we can work out what that power is through P is equal to IV. So I being the current and V being the voltage. Okay, so if I multiply the current by the voltage, it will tell me how much power I have. Now, if I look at this, and say to myself, oh, okay, wait a minute, but what if I put in 1,000 watts of power into the system? In other words, I'm supplying the system with 1,000 joules every second of energy. Well, what does that mean to my current and my voltage? If they are related, if the amount of power is related by the product of the current and the voltage, then obviously, and as you would have seen several times throughout this course and even in maths, if this value here is fixed, then these two values you can play around with, okay? If this was 1,000 watts and I'm transmitting 1,000 watts at 500 amps and 2 volts, 2 times 500 is 1,000. Fine, that works, okay? You can do that. But what if I change it around a little bit, okay? What if I transmit at 10 volts and 100 amps, okay? Again, you keep your 1,000. Now, what that that gives us the conservation of energy thing that we so love in science, okay? So we know that if we can somehow take the power that we get out of the station and crank up its voltage, we know that its current will have to come down, okay, in exactly the same ratio as the voltage goes up, and vice versa. It goes both ways, obviously. Now, so why is that important? Well, if we could figure out a way of changing voltage and making it go up and down, we can take advantage of another thing that we've also worked out, and that is that power is also not only related to the current multiplied by the voltage, but it's also related to the current squared multiplied by resistance. And right here, you say to yourself, well, ooh, maybe you can think already of a reason why stepping your voltage up dramatically would reduce the amount of power that you lost in simply getting it from point A to point B. You see here, I've drawn these transmission lines really short because the board isn't very big, but in reality, obviously, if you've driven through the country and seen those high tension power lines, they go on for miles and miles and miles, okay? Even kilometers too if you're using metric. So those lines represent, no matter how well they transmit electricity, they still add up to a lot of resistance, okay, over huge distances. And so what it would mean is if you just transmitted your power at high currents and moderate voltages, that half your power would be lost before it actually got to the city. Now, don't forget, when you're burning fuel to make that power in the first place, you kind of want to get value for money there. You don't want to be burning twice as much coal or oil than you need to just to get the power that you need up at the other end. So there is a way of protecting the system and stopping those losses. The way we do it is we use transformers, okay? So a transformer, here's one I prepared earlier. Wait, let me do this as like magic. Here's one I prepared earlier. There, how magical is that, right? Okay, so this is a transformer, all right? All it is a iron core. It's incredibly simple. I mean, you would expect it to be incredibly simple. It's been around for like a really long time, okay? You tend to invent simple things first and then get to the complicated. So basically, here we go. This is a transformer, all right? So it is as simple as it looks. Let me turn it around here because somebody's actually torn the protective paper layer off this coil here. Yeah, it's all about coils again, isn't it? So what we do is, we've noticed or realised through a little bit of science work that if you create an iron core, okay, so this is really heavy, there's an iron core, and it has to be iron, not copper, not aluminium, not anything, it's iron. Iron works the best, all right? Why does that? Look it up, okay? There's not enough time to explain every little thing. All right, so iron core. Now, wrapped around one side, you'll see lots and lots of loops of very thick wire. Here's a close-up. Close-up, okay? Very thick wire. On the other side, you'll see it's thin wire, but there are almost infinitely more coils, okay? So that's how basically it works. If you have few coils on one side and many, many coils on the other side, this is what the apparatus that we use to step voltage up and hence current down, okay? So you have in this orientation, you'll see I've drawn on the board there, transformer 1 is a step up transformer. It's a step up transformer because where it takes its power from is from the station, over on the left side of the coil. And you can see I've clearly drawn on the left side of the coil, few coils, few little turns, okay? On the right-hand side, there are many turns, okay? So what's happening here is, in this case, this is in the orientation of a step-up transformer. few coils, many coils, just like on the board, all right? Over on the other end, the electricity, the power, finally gets to its destination, and once it gets to its destination, you need to, nobody needs like 100,000 volts or 50,000 volts into their laptops or into their houses, right? So what we need to do is we need to step the current back down, or step the voltage back down, the current back up again, okay? And so the way we do that is instead of using a step up transformer, we use a step down transformer to bring the voltages back down again. Now I'm going to go into detail about these things in a minute, but here's the difference between a step up transformer and a step down transformer. Okay? Here, this is a step up transformer. Over here, few coils, many coils. Okay? Now, if I flip it around like this and bring it over here, now it's a step down transformer. Did you notice? It's the same transformer. That's right. Just depends on which way you orientate it. They don't have to be identical transformers on both ends. For example, you might want to step up the voltage to a certain amount for transmission, and then when it gets to the other end, you're like, well, I'm going to step it down in stages. I don't need to step it all the way back down to 240 volts, which is why you would notice such things as substations that are out there that are part of the system, part of the grid. So these transmission lines end up at substations, really. So the substation will take the power and start stepping it down, and then the substation will transmit that to the power poles, or, you know, most suburbs are starting to go to underground cables now anyway, but there'll be other transformers, like sort of pole-based transformers that are very small comparatively, and then they step it down the rest to make it ready to get into the houses, okay? So that is the transmission system. The reason we do it, again, is because the higher the voltage, the lower the current. And if the current is really, really low, then the loss of power in these lines in transmission is minimized. That's the whole point, okay? All right, and we do that with transformers. Okay, so power comes out at some voltage. It is stepped up dramatically. It is transmitted with very little loss, okay? And then it hits the step down transformer where it's stepped down to consumer level, where you can use it in your house. And there you go, it goes into your house and you're happy because your internet works and everything's good, your air conditioning works and all that great stuff that electricity gives us, okay? So now to the notes. Transformers and transmission. Formulas that are going to be really, really useful to you, okay? So a couple we've already explored are the power formulas. So we've got P equals VI. So voltage multiplied by current gives you the amount of power that's coming out of the system, and that unit is in either joules per second or watts, okay? And that is the same for anything that gives you power. Again, cannot stress enough how important it is for you when you're looking for something, when you've been asked to find power or current or voltage or whatever it is, or work done, anything like that, that you have spare a conscious thought to what are the units of what I'm looking for exactly. So as in the previous chapters, making errors like calculating force, which is in newtons, when the answer box in a assessment task clearly says coulombs, all right? Or, things like that you should really be able to avoid by asking yourself, well, what exactly are the units of what I'm looking for? You know what you're actually trying to calculate. So that's why I'm giving you both of these units, because occasionally you'll be asked for things like, a searchlight provides 100 joules of energy per second. How many photons are coming out of it? Things like that. And so you've got to say to yourself, joules per second. So it's a light that's set at 100 watts, okay? That's what it is, okay? So things like that. Questions like that are designed to test how deep your knowledge is of what you're actually trying to study. So that's one version here. And we use this often in our calculations for stepping up and stepping down voltages as per the current. And then this formula here, I squared R, okay, it's like the worst I ever. I squared R, we usually use it to calculate, and again, it's in joules per second or watts. This is often used to calculate how much power is lost in the lines, because usually in a question you'll be given what the resistance in the lines is, okay? You won't know the voltage or you won't know something else, but you know, the values of the current and the resistance are often given to you there, or you find them quite easily, and that tells you, well, oh, if I produce 1,000 watts here and I lose 100 watts in transmission, then I know up at the other end there's only 900 watts left. Okay, so it has to be logical. You tell a story when you study physics. That's what physics really is. We've got maths, and you only really learn maths to be able to describe the things around you. And how do you describe things? Well, you describe them like someone telling a story, okay? So you have to create a sort of narrative when you're working these things out and say, oh, if this is where we start and this is where it goes, it has to actually make sense, all right? And that's the best thing that you can do in physics, tell a story of what is going on. All right. Okay. So these are the two main formulas, and there's one more called for power called P equals V squared on R. Okay. P equals V squared on R. That is another one that can be useful if you have voltage and resistance, but you don't have current. All right. And of course, the usual sort of transpositions and sort of things that you can do with those. Yeah, feel free to do that. Now, there is this nifty little one right here, which is kind of important to understand what is up with that. Okay, so I'm going to rub this out because I write way too big to leave everything on the board at the same time. This here is, I'm going to write it nice and big, N1 over N2 is equal to V1 over V2 is equal to I2 over I1. Yes, these two are opposite to the others, okay? Now this is basically how you analyze values, the values that make up your transformers. Whether you're trying to pair up currents with voltages, or the number of turns in the coil with voltages, or the number of turns with currents, any combination that works for you, you can actually do with this. Now, this is obvious to me, but you would never actually try and put numbers in every part of this equation and try to solve it. There's no such thing as solving an equation with more than one equals in it, okay? You'd have to pair up either these two, or these two, or these two, or these two, any combination of a set of values will work, but you can't have it in this form. That just won't work, okay? Now, there is another version of it, okay? There is another version of it, which is where 1 is replaced with the word primary, okay? So you'll see this version. Now, I like this version better personally because it's kind of what I'm used to, but it also is better at explaining what's going on, as in what is the primary, what is the secondary, okay? So, NP over NS. Primary and secondary. I'll get to what they mean in a second. V primary, V secondary, and I secondary over I primary. Okay. Now this makes sense where the currents are the reciprocal of the other two, is because when you think about it, when you go over to P, can you see it over here? P equals IV. If current goes up, voltage goes down, okay? So when one ratio increases, the other one decreases, all right? So that makes sense there in the context of power equals IV, where one has to go up if the other one comes down because you are providing a set amount of power, all right? Okay, so whereas the number of turns to the voltages, they are exactly in the same ratio. So this formula here tells us this, that if you can see my transformer here, the side of the transformer that is accepting the current, okay, that's the primary side, okay? So that's your primary side. I'll write it, primary, primary, okay? Now, the power is then shifted across the transformer into the other turns, all right? And I'll explain that in a second. That becomes your secondary. So the primary always accepts the power, and the secondary transmits it away again, okay? So this is the secondary, all right? Now, what I'm going to do, the primary accepts the power or electricity from the source, okay? So it accepts it, it does its job of stepping the voltage up and the current down and sending it across the system. Now, when it reaches its destination over here, notice that this side of the coil is accepting the current, okay? It is accepting the power from the transmission lines, okay? So now, because it is the part of the coil of the transformer that is accepting the energy, that becomes the primary. It does its job of stepping the voltages back down again and the current back up by doing its thing and inducing a lower voltage in the secondary part of the transformer. So that's why this is now the secondary. Alright? Notice the transformers themselves are exactly the same thing, they're just flipped. Here you can see a couple of, here's a handheld transformer for a much smaller application. These are the ones that I mentioned earlier. There's actually one out on the street just over there. Actually, wasn't it last year or the year before it exploded and caught fire? Because there's a lot of heat generated in these things. Alright, there are a lot. As the current runs through a transformer, it creates all sorts of what we call eddy currents, and they dissipate, they create heat and power loss inside the transformer. So you will see in the questions that you're expected to do, often referred to as an ideal transformer. An ideal transformer doesn't really exist, okay? Not unless it's bathed in, liquid nitrogen or something, right? So there's no such thing as an ideal transformer in real life. An ideal transformer is just a little heads up to you to say that every joule that you put into one side will come out the other side. That's what an ideal transformer is. And at year 12, high school level, that's enough, because you're more worried about figuring out how these things work rather than the reality of actually building them and using them. That comes later, okay? So, as you can see, the operation of a transformer, in this diagram here, this is given to you as a power source. Now I'm going to give you the explanation of exactly how they work, all right, and what they rely on. Over here, you have what is a symbol for an AC power supply. That's kind of important, okay? You can't use a transformer with a battery, okay? The reason you can't use a transformer with a battery is because a transformer relies on a constantly changing flux. Alright, so every time the flux increases and decreases, you end up with magnetic fields wrapping around each individual turn of these wires here, and those fields will, as the power supply goes up and down, changes direction constantly, this is constantly washing this coil with a magnetic field that is coming out of this coil. Okay, that's the key, right? So every time the AC current peaks and then peaks, goes to zero, peaks the other way, goes to zero, keeps on doing that, you end up with a pulse of magnetic field emanating from these turns, all right? That pulse engulfs the turns of wire on the other side. And it is As simple as that. Basically, if you create lots and lots of magnetic fields with lots and lots of turns on this side, all right, that wash over fewer turns, all right, on this side, then your voltage steps down, okay? So, I don't know if I explained that very well. If 100 wires are creating a magnetic field that is washing over here, but there are only 10 wires to pick it up. So if there are 100 turns creating and washing over, and there are only 10 turns on the other side to pick that up, all right, the effect is that the voltage that you put in is stepped down, 10 to 1, okay? So 100 to 10, yeah, you know what I mean. All right, so that way you'll often see these you will often see in questions that you might be given 100 turns on one side and 10 turns on the other, okay? So it is 100 to 10, which is 10 to 1. That is really 10 to 1. The effect is the same. It doesn't matter if they give you an actual number of turns or if they just give you the ratio of turns. You use them the same, because it doesn't really matter. If you think about it for a second, you'll notice that 100 divided by 10 and 10 divided by 1, they're the same thing, okay? Which is why it does not matter if they tell you exactly how many turns or if they just give you the ratio of turns, all right? So, the key here is that it is really important that it is an AC current that is being supplied. Otherwise, if you supply it with a DC current, what will happen is, and they do hit you with questions like this occasionally, where what will happen if I replace the AC power supply with a DC power supply? And then what you should say is that, well, once the DC power supply is attached and then switched on, there will be a pulse of current through the secondary coil, and that will then reduce to 0. And that was where it will stay, because a transformer relies on a changing flux, a changing flux through the turns to induce the current on the secondary side of the transformer. All right, so that is, in a nutshell, how a transformer works. And yes, it is insanely simple and something that we've been using for a really long time. Here is a useful result to look at. I'll kind of write it nice and big so that you can see it. But what we can see here is power into a transformer, an ideal transformer. Power into a transformer is the same as the power out of the transformer. And this is a reality that is relied upon a lot in a lot of questions. In other words, you'll be asked to analyze some part of some value in the transmission lines, or perhaps in what's happening on the end of the user after the last transformer has been gone past the last transformer. But of course, you won't have enough information to do that, and so what will you have to do? Well, you'll rely on the fact that the power into the system is the same as the power out of the system. It is not to say that there are no power losses and that the power that is supplied by transformer 1 is exactly the power that is received by transformer 2. That is not what I'm saying. What I'm saying is that the power received by transformer 1 will be the same as the power put out by transformer 1. What happens in the transmission lines is a different thing. In the transmission lines, you will have a loss somewhere, okay? All along those transmission lines because of their resistance. So the power put out by transformer 1 will be, say, 10,000 watts, but you might get 9,990 watts arriving at transformer 2. Why? Because the lines that transmitted that power got a little bit warm on that on their journey, all right? And that's where some of that energy went, okay? So that is one of the most common errors students make, is when they're not sure of how it all works, is what they'll do is imagine that the power coming out of transformer 1, oh, because it's ideal, has to be the same as the power going into transformer 2. That's not the point. The point of the transformers is to reduce, I mean, obviously it'd be great if you could reduce your losses to 0, but that's not going to happen. So you would expect some loss in lines. Okay, so power in equals power out. This is the same as, now if you know that power is equal to IV or VI, as it's written here, that means the voltage in the primary, so the first side of the receiving side of the transformer, multiplied by the current in the receiving side of the transformer, has to be the same as the voltage in the secondary side of the transformer, multiplied by the current in the secondary. So what I'm getting at here is if the voltage is kind of low and the current's kind of high, and then you run it through your transformer and then the voltage goes really, really high and the current goes really, really low, the products should still be the same, all right, in an ideal transformer, okay? All right, so if you take that result there and then kind of do a little maths to it, divide both sides by voltage primary, I end up with this. Current primary is equal to voltage secondary, current secondary over voltage primary. And then divide both sides by current secondary. What do I get? I get this. Current primary over current secondary is equal to voltage secondary over voltage primary. It is that, as you can see. So it's the major part of the transformer analysis equation that you're supposed to use throughout this chapter. Okay, so you can see that, and then what we do is we use this, and it's of course with a bit more math you add on the number of turns. Number of turns and voltages always line up, okay? So if it's voltage secondary over voltage primary, it has to be number of turns secondary over number of turns primary, because these two are in the same exact ratio. It is only the current that is in the reciprocal ratio, because remember, when the voltage goes up, the current goes down, so they can't be the same. This table here gives you the Australian standard for how voltages are provided and basically what their limits are, okay? You can have a read of that, but generally what it's telling us is how in each state looks like slightly different here and there. In the end, it all kind of turns out to be around 240 volts. Now, there's a term that we use when we're talking about 240 volts. As you can see, this graph infers that we don't really get 240 volts out of our power points. Because our power points are supplying a AC current, it is oscillating between two peak values. As you can see, those peak values are 325 volts peak in the positive direction to what is, if it wasn't cut off by this weird thing, negative 325 volts. Okay, so where does the value 240 volts come from? Excellent question. So how much energy do you actually get out of your power point? You're getting a peak voltage of 325 volts in the positive direction, 325 in the negative, okay? Now, because at some point in the supply of that voltage or in that current, you're supplying from 0 up to a peak of 325, then less and less and less to the 0, then to a negative 325, you can see that what you're getting in your AC delivery of electricity is a very fluctuating amount of energy at each point. So what they wanted to be able to do is figure out what is the average voltage you would actually get out of that power point, okay? So the average voltage is the same that would be delivered by a DC power supply of say 240 volts, okay? So if you supplied your house with a DC power supply of 240 volts or 230, it's always a bit hazy, it would be the same as supplying your house with an AC, supply that goes up to 325 and down to negative 325. Okay? So, to calculate between the two values is actually really, really easy. We use the root 2. Now, something you need to keep in mind with root 2. Root 2 is bigger than 1, okay? Because it's bigger than 1, if you multiply something by root 2, it gets bigger. If you divide something by root 2, it gets smaller. Well, the answer gets smaller, okay? So that's how you make sure you're doing the right thing. So if you're given a question, and what we can do here is just show these values. If you're given a question that says you have a voltage supply of EMF of 325 volts peak. What is the RMS value? Okay, so what is the RMS value? Well, the RMS value, you grab a calculator and you take your 325, and you know that if 325 is your peak, it's the big value, obviously, okay? Which means your RMS value will always be lower, okay? So if I take my 325 and divide it by the square root of 2, I get 229.8. 229.8, which rounds up nicely to 230 volts. RMS. What does RMS stand for? Root mean squared. That's what it stands for. Root mean squared. It doesn't matter what it stands for. Basically, it is the factor by which you multiply or divide your values of voltage and current to give you the reciprocal version. All right. So if you want to go from the RMS or root mean squared of the value that you have to the peak value, you'd multiply. If you want to go from peak to RMS, you divide, okay? There's only one other little complication. Occasionally a question will slip this in just to get you, all right? They may refer to peak, all right? If they refer to peak, then it's not 325, okay? It's 650, because peak to peak goes from a positive 325 to a negative 325. The difference there is double, okay? So you've got to keep an eye out for that, all right? Anytime there's a mention of peak to peak, here you go, the peak to peak voltage is defined as the difference between two maximum, all right? You just got to make sure that you're actually answering the question that is being asked, all right? Okay. So don't forget that, root 2. Did I put it on our help sheet? Yeah. Here's the help sheet and I chucked it on there. As you can see, RMS to peak multiplied by root 2. That's it. The rest you can figure out from there really easily, okay? So from peak to RMS, you divide by root 2. If it's peak to peak, you halve it, then do it. All right, so all of those things are just basic maths, all right? Okay, so it was there. Lovely. Domestic wiring. Ever wanted to do your own electrical work at home? It's not as hard as it sounds, okay? Completely illegal, but not as hard as it sounds. Here we have a description of how power is supplied, where it goes in your house, what each component in your power box does, all right? Now, this is the kind of information that's important, because occasionally in the whole telling the story of physics, sometimes the examiners will like to put in a question that references what's the difference between the neutral and the earth, all right, of a connection in a PowerPoint. So it's kind of good for you to know that, all right? So what you could do really is just read. I don't want to spend too much time on it because it's not really that hard to figure out on your own. I mean, just by doing a bit of reading. But just to break it down, you have, this is the power coming into your house, all right? It goes to a main switch, because your main switch, if you've ever been to the power box in your house, you'll see there's a main switch there, all right? That main switch will isolate the whole house. It completely cuts off power to everything, all right? So it goes into the main switch first, then it goes to your meter box, or to your meter, the meter that, you know, charges you way more than it's worth, okay? Once it goes to the meter box, in other words, it records how much you've actually taken, it goes through your fuses. Now the fuses, in the old days, were a little bit of wire that had you know, I think a higher resistance than your normal wire does, so that if the current drawn through that wire was a little high, it spiked for some reason, that would melt and create a little gap, and it would stop the fire from actually starting in the walls of your house, okay? We changed those with circuit breakers, okay? So circuit breakers are all installed now instead of those fuse wires, okay? Circuit breakers are super interesting. There's a bunch of YouTube videos that show exactly how they work. It's very cool. You should watch them, just for your own knowledge of stuff that's in your house and how it works, right? So why wouldn't you want to know that? So anyway, the fuses, what the fuses do is they protect your property, okay? Now, I don't see it in this diagram, but in addition to your fuses, you'll have a safety switch. The safety switch is a different thing again. The safety switch is there. It's usually only attached to power points. It's not really attached to the breakers that go to your lights, because I'm not sure why exactly, but it's usually just your power points. I think because you're not really meant to be messing around with your lights that much anyway. You change the globe and that's it, right? But when it comes to your power points, if there is some sort of a fault that occurs with your toaster, okay, or kettle, whatever, and all of a sudden the outer covering becomes live, it can obviously kill you, right? So the safety switch is designed to protect life, okay? Whereas the fuses or breakers protect your house from catching fire. Your safety switch protects anything alive that is interacting with electrical components. That's what it's for, all right? Okay, and like I said, you should watch some videos. There's some great little animations and things that show exactly how they work. They're very clever, I must say. Anyway, now, notice, after your fuses, which protect your property, they go through, and you'll see that in your plug, there'll be an active terminal and a neutral and an earth. Notice that both the neutral and the earth are attached to a metal bar somewhere that is attached to the earth. And I can actually, when we get back together, remind me to do this, I will show you where the earth wire that connects every power point in the school actually goes. It's over there. Okay, but I'll show it to you. It's pretty cool. It's really thick because there's so many power points, right? Anyway, so in your house, what your electrician will have done is found a copper wire that the plumbers put in for some water supply, and any copper wire that's gone down into the ground, and basically attached a green and yellow wire with a little bracket to that copper pipe. That copper pipe goes into the earth, and that's the earth. It doesn't always make sense why the neutral and the earth are both connected to the same component, the same metal bar that goes into the earth. And that is basically because what the neutral does is it completes the circuit, okay? So it completes the circuit so that there is a flow of current, and it completes the circuit where it's meant to be, all right? So as a component is working, as a machine or whatever is working appropriately, then the active is live and the neutral takes the voltage down to zero, okay? So there's sort of, as we discussed earlier, there's nothing left, basically. It completes the circuit. Now, what the earth is connected to is the actual skin of the machine that you're using, whether it's an electric heater or whether it's a toaster or whatever, okay? So you have your toaster and the wire comes in, the active comes in, it goes through and toasts your bread, and then goes out to the neutral. Neutral's set at zero potential, okay? So this comes in at 240 volts, goes out at 0. Beautiful, okay? Everybody's happy, electrons moving along, okay? Now, over here though, just in case this wire here breaks somewhere along and in the operation of its in its operation, and all of a sudden this active makes contact with the outer skin of your toaster. Okay, now if it makes contact with the outer skin of your toaster and it's got like some nice little rubber feet so it doesn't slip, then technically there's nothing happening there except until you come along and touch it. And when you touch it, then the active delivers its 240 volts, hits the skin of the toaster, your hand, through your body, through your heart, and into the ground, and that's the path of the electricity, which is not good, obviously. So, if you've ever experienced this, and if you haven't yet, you will, because it happens. When a breaker goes off, when you've gone and pressed the button on your toaster, okay, you press the button on your toaster and the breaker goes, and you're like, oh, what's going on? So you go out and the breaker slip. Oh, okay, so you switch the breaker back on, go in and put your toast back in, and the breaker goes again. You're like, all right then, there's something wrong with my toaster. What's wrong with your toaster is something's gone wrong and it's trying to make the outside of the toaster active or some other part of it, okay? But what we've done is we create a way out for that current, okay? So that way out is your earth wire, and it goes off and joins on to the same place that the neutral does, into the earth. All right? So now the skin of the toaster has become active, all right? So as soon as you close the circuit with your body, you die. But instead, now, when you go to switch it on, instead of making the skin active, the current now flows through here and bang, out. Because it offers almost no resistance, because it's just a naked wire, okay? Because it offers almost no resistance, you know from voltage equals V equals IR, right? If you've got 240 volts coming out, okay, and you've got almost zero resistance, what's your current going to be? Your current is going to be like huge, all right? Your current becomes huge, and that's what these breakers respond to. They respond to these huge currents, because huge currents means a lot of heat, and that's what causes things like fires and problems and death. So, all right, okay. So that's the system. That's how it's designed to protect you, and why also it's highly illegal to do your own electrical work, because a lot of people, common sense isn't really as common as its name leads you to believe, and so guess what it's time for? It is time for questions. Now we've got a bunch of examples here. There are a lot of examples, and as usual, I have spent a whole lot of time working through many of them with adding lots and lots of notes, because it's a really useful way to teach the topic. All right. This is a typical setup. Things that you do need to notice, all right, when you're looking at a question like this. What do you need to notice? Well, let's see. I need to notice that I have an AC power supply over here. I have transmission wires. There is no transformer over here. Just one over there, right toward the globe, okay? This is a really typical setup, all right? Often the questions will be pitched at you with a single transformer. And if the question is a sort of deeper type question, it may move into, oh, well, how would you fix this problem that, obviously power loss is a problem. Okay, so if we have a very quick look at this one. To model an AC transmission system, students set up their experiment as shown below. They set the output of the power supply to 20.8 volts RMS, So all of these little things are important to you, okay? 20.8 volts RMS AC. It's AC, which means the transformer will work. 20.8 volts RMS, okay? RMS is good. It's as though it's a DC power supply at 20.8 volts, okay? Now, that supplies a transformer past these long transmission lines that then lights up a globe, all right? So, let's see. They set the output of the transformer 20.8 V RMS AC. They use a 10 to 1 step down transformer. Okay, why? Because the globe is only little. It only needs 2 volts. If you hit it with 20 volts, it's just going to burn out. So how are you going to fix this? You're going to go spend a bunch of money on a transformer, okay, to light up a single 2-volt globe. All right, so your transmission lines are of 2 ohms each. Something that I want you to do is notice this thing here. If the power lines have enough resistance that you can count them as resistance, then I want you to imagine 2 big resistors here, okay? So there's 2 big resistors, there's a power supply here, okay? So this is what I want you to imagine. Because this is super important to getting these questions right. Now, I want you to look at this coil as just being part of the circuit. It's just a wire, okay? So you've got a power supply, wires, and a couple of components here that use up, that will drop voltage over them, okay? What you're looking at here is a series circuit, okay? That's what it is. If you treat it as a series circuit, this whole section here as a series circuit, then it means that you know one really important thing. That the current in this line is the same everywhere, okay? Anywhere I measure the current, okay? Anywhere I measure the current in this loop, it's the same. Why? Because it's a series circuit. What are the rules of a series circuit? Well, the rules of a series circuit, each component will drop a certain amount of voltage depending on its resistance, but what's the current in the circuit? Well, it's the same everywhere. Why? Because the current's made of electrons, right? So if you either have an electron or you don't. It's not like they disappear, okay? So this becomes a series circuit where you don't know what the voltage, you know that 20.8 volts have been supplied, but you don't know how much have been dropped over each line, okay? You don't know anything else about it, but one thing you do know, the current. If you can calculate it, if it's given to you, whatever, you know it's the same everywhere through there, okay? Of course, not on the other side. On the other side, because remember, that's the whole point of the transformer, is it messes around with current and voltage, so obviously the current's not the same on the other side, but it is within the same loop. Okay, even when you look at my other example, in this example where there are 2 transformers in place, you have a current in the primary, which will correspond to a different current in the secondary. But that current is the same from everything from this coil, okay, from this coil all the way through here, through this coil, okay, and back again. Anywhere you measure the current in this loop, it's exactly the same. Why? Because again, these wires are acting like resistors, so they're like their own components. There is a single line that goes from the secondary of the first transformer through those long lines to the primary of the second transformer and back again. They're all connected. There is no connection between the turns on this side and the turns on this side. If there was, it wouldn't work, okay? So, this is an isolated system, one line, okay? You can see if it's one line with all the components attached to each other, that makes it series. So you know the current is the same everywhere. But is the voltage the same everywhere? Well, no, it's not. The voltage that is supplied by the secondary of the transformer some will be lost here, some will be lost here, okay? And then whatever's left will be here, okay? These will act like one big component in the series circuit, and whatever voltage is not being dropped over these lines will appear here at the primary. And then that really high voltage, whatever it is, not quite as high as what left, will then be used to create the secondary voltage. In other words, the step down into the other part that goes into the houses and, you know, PlayStations and whatever. They use a 10-to-1 step down transformer at the other end. The output of the transformer is connected to the globe. The globe is operating at 2 volts and 4 watts, okay? Before connecting the circuit, the student tests the power supply by connecting it to an oscilloscope as shown below. I've shown you what an oscilloscope already looks like, so we don't need to go into that again. What signal will be observed? What signal will they observe on the oscilloscope? So, the oscilloscope gives you, it says 20.8 volts RMS, but the oscilloscope is going to give you what the actual graph looks like, okay? Which is why 20.8 volts RMS is equivalent to a 20.8 volt DC power supply. So to get that answer, you need to actually use the RMS conversion, and that's all it is, okay? So root 2 times 20.8, you get 29.5. Now, there is no 29.4, sorry. There is no 29.4 peak. Notice that they put this option in here. A lot of students will go for that option, okay? Because they're not, you know, you're panicking, it's an exam, whatever. 29.4 peak to peak, that is not correct, all right? So you need to look again. It's 58.8 peak to peak. There is no 29.4 peak, all right? Which is why you end up having to double it to get one of the options that are offered in the multiple choice answers, okay? So that's where that comes from. All right, so if we look over here, a 50 hertz AC power supply is connected to a circuit and an RMS current of 0.5 amps is observed to flow. All right, so it says an RMS, so that is 0.5 amps, okay. Which graph best represents the variation of current with time for the circuit? Okay, now, the reason it's D in this case, and I've got a little bit of an explaining thing there for you, you need to match up 2 things. You need to match up the current, and you can see that it's 0.5 RMS, which means you need to multiply by root 2 to get the peak current. Okay, so it works on both peak and voltage. Now, that gives you the 0.707, which is the correct value on the axis there. And there's a couple of 0.7 values, but why is it this one and not this one? Why? Because here they've given you the 50, and this is aimed at students who don't know what 50 hertz means, all right? 50 hertz means 50 cycles per second. So the formula for that is this. The period is equal to 1 over the frequency, okay? That's all that is. That should be on your help sheet as well, and you should practice using it a couple of times before you get anywhere, all right? So 50 hertz is 0.02 seconds. So in other words, a full cycle every 0.02 seconds. That's why there's the peak 0.7 and the period. That's how you get that question, all right? It has been found that for a transformer, the ratio of the power output to the power input is, now which one is the most correct? Often you get these multiple choice questions and you've got to find the most correct option because sometimes they're not, even the one that's right isn't great. Okay, less than 1 in all cases because of heat losses. That does ring very nicely true. It is obviously the right answer. Less than 1 only if it is a step down transformer. Why? There are going to be losses in all transformers. There's no reason. More than 1, no, that's silly. You're creating energy. More than 1, yeah, there is no more than 1. Okay, you don't get energy out of nothing. All right. Now, let's have a look at this one. All right. A village has a maximum electrical power requirement of 100 kilowatts. Again, be very careful with the kilowatts and the microseconds and the kilometers and all sorts of stuff that they throw at you. Okay, 100 kilowatts, 100,000 watts. There's 20 kilometers from the village, which generates electricity at 250 volts RMS at a frequency of 50 hertz. It gives you everything, right? This is converted by a step-up transformer T1 to 22,000 volts. Okay, so in other words, what you're looking at here is 250 volts go in, all right, and 22,000 volts come out. Okay. All right, 22,000 volts hit the transmission lines. Now you know they're not going to have zero, they're not going to be zero resistance, right? They're actually, it says a total resistance of 2 ohms. In other words, they're 1 ohm each. Doesn't matter though. You always consider them as a set, all right? As a sum, all right? So, 2 ohms and converted back to 250 volts RMS by a step-down transformer over here. So, 22,000 volts pours into these lines, okay? Then a little bit of it is lost. What's left, which is like 21,900, whatever, goes into the primary of the second coil, of the second transformer. Then there's a certain number of turns here to make sure that whatever got there comes out at 250 volts, because that's what the houses need. All right? That is how you interpret what is going on here. Okay. The village must get 250 volts RMS to function. For 250 volts to be stepped up to 22,000 volts, we need a transformer with a ratio of 22,000, as you can see here, 22,000 divided by 250. It tells you what the factor is when you do that, okay? All right, so with a transformer of a ratio of 22,000 over 250, so you need a ratio that is 1 to 88, all right? Okay, 1 to 88. Now the question goes and asks, a number of different transformers are available for use as transformer 1 in the system. Their characteristics are shown below. So notice, even though there's a whole bunch of stuff you can infer from that diagram, there is no interest being paid to what voltage arrives here or any of that, okay? All they're talking about is to get 250 volts in and then 22,000 volts out, what kind of transformer out of these do you need to use? How do you know? Well, you need to know what the ratio is. So how do you figure out the ratio? Well, if 250 went in and 22,000 came out, 22,000 divided by 22,250 is 88 to 1. Okay, so here you've got to find one of these ratios that is 1 to 88. Let's see, did they give you, yeah, they gave you B and C, okay? So, either you realise, oh yeah, it's just a ratio question, but not sure what step up and step down means, and that is why they've given you both of these to see if you know the difference, okay? So over here, 44,000 to 500 would be 88 to 1, okay? In other words, it would be stepping down, not up. All right, and that's why it's C, because in this version it's 1 to 88, and you've got to be kind of like awake enough to realise you need to do a division to figure out what the ratio is. Here we go. The apparatus shown. You need to notice the little deets, the details. Okay, there's a battery there. What did we just mention about batteries and transformers? That's right, they don't work. Okay, why? You close the switch, there's an initial pulse. You open the switch, now there's another pulse. Okay, only when there's a change in flux do you get any kind of EMF induced. All right, so you now have to find the appropriate graph that describes this. So you're supposed to look at that and go, oh yeah, that's not going to work, but we are going to get a couple of spikes. All right, so which one? Let's see. It says which pair of graphs. Which pair of graphs work? Let's see. Yeah, okay, so the way this is set up is there's a pair, there's a pair, there's another pair. pair, all right? So it's this pair, obviously, since I circled it, but why? You close the switch. Before you close the switch, there's nothing going. Close the switch, there's an increase in voltage through the primary coil. In other words, that coil becomes live, all right? So you end up with, if you go to measure the voltage on this, yep, it's whatever the power supply says it is, okay? Because it's closed and it's open. The switch is closed, current's running. What's happening in this coil though? In this coil, as soon as you close it, there was a wash of magnetic field lines that then stay where they are, basically, stay switched on. So you get a little spike. Now, when you open the switch sometime later, the voltage through this coil drops to 0, and you get another change in flux, where it goes from full flux to nothing, and you get a second spike. Obviously, closing and opening, so filling and emptying, give you spikes in different directions. Lenz's law, that's why it had to be this. All right? Not that, or anything else that's weird. Okay? There's a nice explanation there as well about why. This is example 9. The diagram shows a model of a transformer in a circuit. All right, so again, interpret what you're looking at. AC power supply, good, transformer will work. This is a step-up transformer. How do I know that? Well, I'm supplying a few coils to create a field that wash over many coils, okay? So that is going to give me more voltage out here, all right? So in this transformer, the voltage will go up and the current will come down, okay? And there's a resistor in this circuit here, okay? So there's something there, whether it's a heater or a light or whatever, who cares? It's just some resistance, so it doesn't matter. All right, which of the following correctly identifies part 1 and part 2 and the function of this transformer? Okay, so part 1 is the secondary coil. Notice, part 1, that's the secondary coil, because the secondary coil is the one that takes the voltage and changes it. Part 2 is the primary coil. There's part 2. Yes, that is the primary. The primary always takes the voltage in the first place. Okay? And what is the function? Is a step-up transformer. Well, yeah, few coils, too many coils is a step-up transformer. Okay? That, and everything there is explained as to why. Some mobile phones are recharged at a power point using a charger that contains a transformer. What is the purpose of the transformer? This one's interesting. The purpose of the transformer isn't to change. See, a transformer doesn't change a current or a voltage from AC to DC. Something else does that, okay? But the purpose of the transformer in your charger is to decrease the AC voltage down from the power point value to what your phone can take, all right? So, in other words, your phone does not need 240 volts or power supply to 240 volts. It'll, melt it, okay? So the purpose specifically of a transformer is to reduce the AC, okay? There are other components that rectify and turn it into a DC so that it can operate with the battery, okay? All right. In this question here, you have notice the battery, okay? That would make, if there's a battery in this circuit, there's a transformer. This is the symbol, one of the many symbols of transformers, okay? There's the primary coil. Why is it the primary? Because it takes the electricity, it takes the charge in the first place, okay? Switch it on. Whatever this component here will work nicely. Will this component work? Well, no, it won't, because this transformer requires an AC supply to make it work. Okay, so you can see that already. I'll leave the rest of that for you to kind of look at. And there's a lot of explaining there, as you can see, if you get stuck on that one. Oh, here's an interesting question. In this graph, you're given the voltage and the current plotted against each other, okay? So you can see what voltage you're being supplied, what current is supplied. It's a peak value, you can see. take notice of the graph, it goes up, it's really going up in ones. 1 volt, 2 volts, 3 volts, 4 volts, 5 volts. So there's a 5 volt supply, peak supply, and a 3 amp current supplied. Okay? The question, what is the RMS voltage across the speaker terminals? Well, yeah, just work it out. Divide by root 2 to give you what the RMS is. That's not the interesting part of the question. What is the resistance of the speaker? Okay, to figure out the resistance of the speaker, you need to know the current you need to know the current and the voltage, and then solve for the resistance, both of those are given, okay, in the graph. So what I did here was to just show you that whether you're using the peak values or the RMS values doesn't really matter as long as you don't mix them up. If you use the peak values, as you can see, 5/3, 1.67 ohms, okay? Here, I've just done the same calculation using RMS values, and the RMS values, which I had to calculate the current RMS first, and then I put the RMS value of voltage over the RMS value of current, and I got the same value, all right? So they are consistent with each other, okay? I mean, if you think about it mathematically, the root 2's obviously cancel out, and that's why, but that doesn't matter. Okay, this is something that's not really focused on, and I've never seen a question like this in an exam, and you know, in all of the time that I've been looking at this stuff, but you know, Colin's put it on here. It might actually be part of it, but I need to go back and look at that. But the resistance is equal to the resistivity of a material, okay, multiplied by the length of that material divided by the cross-sectional area of that material, okay? So if you can understand this sort of basic maths there, the only thing to really know about this is that the resistivity of a material is a value that is set for a particular material, okay? And when you're using it for, say, steel or copper or aluminium, whatever, that value there will be the same for the whole thing. Okay, so here it says, just to show sort of what they can possibly ask you, a conductor of length 10 centimeters and a uniform diameter of 1 millimeter has a resistance of 100 ohms. Calculate the resistance of a conductor of the same material with length 20 centimeters and a uniform diameter of 2 millimeters. Now, what they've actually essentially done there is they have doubled the length, okay, and they have doubled the diameter. So what you need to do to answer a question like this is ask yourself, what effect would changing these two values have on R? Now notice, what I've done here is I've worked out that by doubling the length, all right, L becomes 2L, all right, and that's shown here in the same formula with a double length, okay? And increasing the diameter by doubling it essentially increases the radius by double, okay, so doubles the radius. And when you double the radius in calculating area, because area is a squared relationship, when you square R, when you double the radius, you quadruple the area, okay? Which is why you end up with 4 times the area in the denominator. Notice, the resistivity does not change, okay? The resistivity is a constant, all right? And it makes no difference to the eventual calculation of R. So what happens to the resistance of R? It effectively halves 2 over 4 in 1 over 2, so it's a half, okay? So, yeah, incredibly rare, never seen that actually used in a Sakura thing. Right? As I'm sort of scrolling through these questions that I detailed in the notes, the ones that I've left blank are just, versions of the things before them. You'll notice that, yeah, there's a lot of detail in here. So what I'm going to do is I'm going to leave it there. Okay, so it's just one lecture with a few questions. Let's see, I've left the rest of all that. Okay, feel free, as usual, to ask anything, anytime about any of these questions. and set up a WebEx meeting to just personally talk about particular things. Go through the lecture, go through the questions yourself, do as much as you can to try and understand this stuff as quickly as possible, because sort of the more you can churn through right now, the easier it'll be to fix up little minor misconceptions and ideas. And you'll find that you learn this stuff pretty easily and quickly by just putting in and trying really hard. Okay, I will see you all again very soon, actually, as we're all coming back. How good's that? No more videos. Oh well. Bye.